Hello and welcome. In this presentation, we will be discussing the problem of finding all triplets in an array whose sum is equal to 0. We will explore the problem statement, the brute force solution, and the time complexity involved, as well as limitations and optimization strategies. Let's start with the problem statement. We are given an array of integers and our task is to find all unique triplets, 3 indices I, j and k, such that the sum of the elements at those indices equals 0. The triplets must satisfy the condition j is greater than I and less than k, meaning the indices should be in increasing order. For example, given the array with elements 0, -1, 2, -3, 1, the triplets with sum 0 are at indices 0, 1, 4 and 2, 3, 4. Another example is an array with elements 1, -2, 1, 0, 5. Only the triplet at indices 0, 1, 2 satisfies the condition. Now let's look at the brute force solution. This approach involves checking all possible triplets in the array using 3 nested loops. Here's how the approach works. The outer loop picks the first element of the triplet. The middle loop picks the second element, ensuring the second element comes after the first. The inner loop picks the third element, ensuring it comes after the second. For each triplet, we check if the sum equals 0. If it does, we store the indices of that triplet. This method guarantees we find all possible triplets, but it's not efficient for large arrays. Here's a code implementation for the brute force solution. The function find triplets takes an array of integers as input. We loop through the array 3 times with 3 nested loops where I, j and k represent the indices of the triplet. If the sum of the elements at these indices is 0, we add their indices to the result vector res. Finally, the function returns the vector containing the indices of all the triplets found. Let's walk through an example with the array with elements 0, -1, 2, -3 and 1. First, the outer loop picks I equals to 0, the middle loop picks j equals to 1 and the inner loop picks k equals to 4. The sum of the elements at indices 0, 1 and 4 is 0 plus -1 plus 1, which is equals to 0. So we add the triplet 0, 1, 4 to the result. Next, for I equals to 0, j equals to 2 and k equals to 3, the sum is 0 plus 2 plus -3, which is equals to 0. So we add the triplet 2, 3, 4 to the result. At the end, the output is 0, 1, 4 and 2, 3, 4, the indices of the triplets with a sum of 0. Now let's discuss the time complexity of this approach. The time complexity of this brute force solution is big O of n cube, where n is the size of the array. This is because we have three nested loops, each running up to n times. For every triplet, we check if their sum equals 0. While the space complexity is big of 1, meaning no extra space is used except for storing the result, the time complexity is quite inefficient for larger arrays. As we can see, the brute force approach works but is inefficient for larger arrays. With a time complexity of big of n cube, the solution becomes impractical for arrays with thousands of elements. An optimized solution would reduce the time complexity to big O of n square using techniques like sorting and two pointers, which we will discuss next. The optimized approach involves sorting the array first. Sorting allows us to eliminate duplicate triplets and speeds up the search for pairs that sum to 0. Next, we use a two-pointer technique. After fixing the first element, we use two pointers to search for the other two elements that together with the first element sum to 0. This method is more efficient and reduces the time complexity to big O of n squared, making it suitable for larger arrays. In conclusion, while the brute force solution is easy to understand and implement, it is inefficient for large input sizes due to its big O of n cube time complexity. Optimized solutions like using sorting and the two-pointer technique reduce the time complexity to big O of n squared, making them much more efficient for larger arrays. The brute force solution, however, can still be useful for smaller arrays where performance is not a major concern. Thank you for your attention. That concludes the presentation. I will now open the floor for any question you may have.